During the first half of the 20th century, after the postulation of quantum mechanics, a new branch of physics started being popular known as particle physics. Scientists were searching for new particles popping up during various experiments. Many scientists were setting camps up above the mountain peaks because some particles, like muons, having low lifetime, don't have enough time to reach the surface of the Earth. In the beginning of 1930s, some physicists got some disturbing results while detecting new particles. This new particle was showing exactly the opposite property to that of normal particles observed in the universe. They were confused whether it was the fault of machines or some human error. Later on, it was found out that for each particle, there is an opposite counterpart known as an antiparticle. So what are these antiparticles and how do they differ from normal matter? Let's understand in this video. My name is Siddharth and you're watching The World of Science. Up to that period, theoretical physics was standing on two pillars, relativity and quantum physics. Quantum mechanics deal with the energy and momentum of the quantum particles. Each quantum particle moves within the four-dimensional framework of space-time, and thus it was necessary to incorporate the theory of space-time, that is, special theory of relativity, with quantum mechanics. English physicist and genius Paul Dirac did this in 1928 and devised the famous Dirac equation. What's surprising from the Dirac equation is that along with positive energy states, it also mathematically showed the existence of negative energy states. Dirac wanted to make sense of the mathematics and thus he applied the theory of electrons and holes to explain this mathematical anomaly. Negative energy states can be understood as the absence of particles rather than presence of particles with negative energy states. No one could have made this assumption at that time. But only 4 years later, Anderson, while doing a particle detection experiment, found something very strange. Particle detection simply involves a target object and a particle is made to hit on them. Depending upon the mass and energy of the particles, they penetrate the target, and difference in depth of penetration is interpreted as different mass, and thus using the parameter of depth of penetration, we can find different particles with different masses. Also, the target object is placed in an electromagnetic field so that the particles hitting the object follow a path towards the opposite charge. Anderson found out that some particles are following exactly opposite paths with respect to the path of the electron. Suppose if an electron was moving towards the positive phase, the anomaly was moving towards the negative phase. This result was not a single occurring event and was later found out that there were many instances in various laboratories but were ignored as human or machine error. But after the Dirac equation, things were about to make sense. This physically deviated energy signature was not any machine error but a real particle with opposite charge with respect to the electron. Electrons are negatively charged, thus moving towards the positive phase. So this new particle must be positively charged and it is moving towards the negative phase. Also, in both the cases, the depth of penetration is the same, thus they have the same masses. Thereby, we have a new particle with the same mass as that of electrons but positively charged. This new particle is the antiparticle of the electron, and since it carries positive charge, it was named positron. The universe is a collection of positive and negative particles in order to follow the conservation of energy, but we see only normal matter all around the universe. This is called matter-antimatter asymmetry. We have explained a few probable reasons for this asymmetry in this detailed video. Click here to check it out. The solution to this asymmetry is still a matter of research, but the presence of antimatter is not only theorized but has been experimentally observed. Each particle and its counterpart antiparticle, when combined together, completely annihilate each other and release energy in form of photons, gamma radiation, and neutrinos. Can we produce antimatter? Well, Antimatter is often produced naturally in space. During the radioactive decay of heavier isotopes, positrons are produced in large amounts. Breaking down neutrons into protons and electrons also produces a little bit of anti-neutrinos along with it. Anti-neutrinos are a common occurrence in the beta decay of radioactive processes. Another occurrence of antiparticles is associated with cosmic rays. They are highly energized rays consisting of gamma radiation that travels at the speed of light throughout the universe. When the cosmic ray strikes the atmosphere of the Earth or any planet, it ionizes the gas and produces a stream of particles such as the production of antiproton in the Van Allen radiation belt. Thus, the production of antimatter is often natural. But we can also produce it artificially. A major amount of budget has been spent in the production of antiparticles in the particle colliders. One of the methods of the production of antiparticle is hitting the high-speed electron on the goal target. Usually, the target particle is taken by the element with high atomic mass. When an electron hits the nucleus of the target, it gets energized, which leads to production of photons. This photon goes through the decay process and it decays into a proton-antiproton pair. Thereby, the law of conservation of energy gets satisfied. Another method involves high accelerating protons that are made to collide with a heavy nucleus. Kinetic energy gained during the process leads to the formation of a proton-antiproton pair. Experimentally, the production of antineutrons has been observed from the collision of two high-energy protons. In 1995, CERN successfully produced the negative counterpart of hydrogen known as anti-hydrogen.
Normally this is rolled over a meter so that these things are in line, but we mix the antiprotons and the positrons, which are anti-electrons, inside this magnetic trap. They create anti-hydrogen, which is then trapped, can't escape. Then we can do any type of experiment we would like on it, shine a laser on it, do this charge measurement, even try to study gravity, but it all takes place inside this superconducting atom trap. That's the business end of alpha.
But what is the need of antiparticles to be produced? It really costs a lot to produce antiparticles. To produce just 10 mg of positron, we need $250 million, and this is nothing compared to the production of 1 gram of antihydrogen that would cost $62.5 trillion. But the production of antiparticles can be very beneficial, like in medical application of treatment of cancer or production of advanced level weapon systems. The very fundamental property of an antimatter particle is that it annihilates when combined with the matter. This annihilation event produces a huge amount of energy that can be used as a fuel for propulsion in futuristic space vehicles. Okay, now we have produced the antiparticles, classified it to use in a particular application, but where do we store it? As we know, the meeting of antimatter and matter is catastrophic. So it is common sense that we cannot store the antimatter in our normal containers. Usually, the particles like antiprotons are stored at a very low temperature and is dispersed in the electron plasma. But the most suitable method used to store antimatter is vacuum and magnetic traps. Depending upon the charge of the antimatter, we can use a particular combination of electromagnetic fields to keep the particle away from the walls of the container. A vacuum is created and antimatter is made afloat in that vacuum, balanced with the forces of magnetic and electric charges. Nature is filled with facts incomprehensible to the human mind, and antimatter is one of them. Can there be a future when we will produce a large amount of antimatter that could propel huge spaceships out of this planet and could run power throughout the Earth for years? We can hope and try to find solutions to produce it efficiently. What are your thoughts about antimatter? Let us know in the comments. If you found this video interesting, please leave a thumbs up and share it with your friends. Check out our magazine Cosmos Now, which is India's first independent astronomy magazine. Link is in the description. Do follow us on Instagram for daily quality content that'll make you fall in love with science. Make sure you subscribe to the World of Science. Until next time, stay scientific.